when recorded in this way. It's nasally, and I'm too close to it. But I can't hear your questions at all when you ask them out there, so I will always repeat your questions so that actually makes it into the discussion as well. All right? Kinematics is an adix, which means it's like mathematics. That last part, that suffix, is the part that tells you that it's the study of. In the same way that ology is the study of, adix is the study of. You should know what the first root of that word is, kina. You've heard of other words that have kina in them. Generally, kina means to move. So this represents the study of motion. The problem is that mathematics and kinematics both have adix in them, and there's a reason for that. It's not really a study. It's more like the rules of motion, in the same way that mathematics is the rules of arithmetic. So when we are talking about kinematics, we are talking about a language and a set of relationships that communicate ideas about motion. This is not physics. I want to start from the very beginning and have you understand that this is not physics. This is the jargon of physics. It's how we will communicate ideas in a clear and precise way. Since it's a study of motion, there are a litany of words that we have to use. These words do not have ambiguous definitions. They are very precise. And because of that, we use them with great care. So you might have definitions for these words. They probably don't match mine. For today, that's all we're probably going to get on the screen when it comes to the terminology we're going to use. Some of these you probably have an idea about. But like I said, we're going to have to dispel some of that. Words that you have used successfully in the past need to be given a clear and more meaningful definition in here. We're going to start with these two words since they likely occupy the same location in your vocabulary, distance and displacement. And although they sound like they should be very similar, they actually aren't that close. Let's make a huge assumption that almost all of you are going to put your head down tonight in the same place where it was started this morning. Would you agree? The vast majority of you will go to bed tonight in the same place that you woke up this morning. At least I hope most of you will. An area of security, happiness, and comfort. Assuming that that's true, that suggests that your displacement for the day is going to be 0. The word displacement technically means change in position. It is a direct comparison between your final position and your initial position. Again, over the course of today, I'm hoping it'll likely be 0. That your final position this evening when you go to bed will be the initial position you woke up in this morning. This is a different idea than distance. They are not necessarily related. Distance is the entire length of the path you took. It's the entire length of that path that you took. If we're talking about comparing this evening to this morning, it's the entire trip you took from the moment you left your bed to the moment you returned. Even if you retraced your steps, you're always adding. It's like the step counter on your watch or the odometer in your car. You're always adding numbers to your distance. It is the absolute path length the object takes from its initial position to its final position. That's its technical definition. Yes, sir?
So if someone were to travel along like a semicircle, then the distance would be around the whole thing, like half of that circle, and then the displacement would be straight across?
It'd be the diameter, sure. Did everybody hear his question? To be honest, these are the words that go along with what we're talking about today. Their definitions are largely going to be in context as we go forward. I still don't know why it does that. I'm gonna go with the classroom ghost is just screwing with me, unplugging the fictitious plugs because no plugs ever change. I don't really know. I have yet to figure it out. I'm gonna claim that my projector is dying and I need a new projector. It's a good claim to make, so I get a new projector. But I don't think that has anything to do with it. So let's go ahead and go on. So yesterday and the day before that, you guys had an opportunity to work with the motion sensor and such. And in so doing, we were producing graphs, pictures of what was happening while you were dancing in front of the motion sensor. Today, I really want to get to the nuts and bolts of this. And although I'm going to start with this today. Now, my real goal is to let you understand that I don't want to teach this. There's a lot of things that you probably don't want to learn, but there's a lot of things that I don't want to teach. The reason I don't want to teach this specifically is that this is kinematics. It's the study of motion, but really, it is what is happening. It's not why anything's happening. And to me, the best part of science is talking about why things happen. All we're talking about right now is what is happening. But there's value in this. And the reason there's value is that this gives us that common vocabulary. It's the result. Look, if I drop a feather or I drop a rock, which one's likely to hit the ground first? I know, because you've dropped these things and you've seen the rock make it to the ground before the feather. Yet, in the next couple of weeks, I have to tell you that they both hit the ground at the same time. Because I'm going to say all these things like we have to neglect air resistance, or we have to assume that they both have the same shape, or we have to assume that we're in a uniform gravitational field, stuff like that. That doesn't have to be true. But we're going to look at fake physics so that you can learn the mathematics behind physics. And then we'll talk about the real thing later, which will break all the rules that I will have set out telling you from the beginning. In fact, kinematics is covered by a lot of teachers for 4 or 5 weeks, going back and forth with graphs and equations and word problems. Look, I want to do this in 2 weeks. 2 weeks only. I want to be done. I want to not talk about this stuff so I can talk about the real stuff in physics. Why the feather takes longer. Not because that is a particularly interesting example, but because talking about objects rolling down a ramp, which is what we'll get to a lot of, is just not that exciting to me. So, you guys understand my point of view now, right? I want to move through this as quickly as we possibly can so we can get to the real stuff. The point of what we're learning now is the idea of describing motion. To be able to take a picture of what we see here and create a mathematical relationship. My goal ultimately in all of this is to create what's called a motion equation. Now this is not what you think it is. This is x as a function of t, position as a function of time. That's what I want to create. I want to have an equal sign here, and I want to have stuff out here that has to do with the way the object moved. That's what I want. In fact, look at just this picture for a moment. Let's pick one of these lines to look at. This one. Actually, yeah, that'll work. Would you all agree this is a straight line? Is that okay with all of you? Now, based on what we've done in class already, this axis is position. And this axis is time. Position is usually given the variable x to describe it, which is why I have a hard time calling this the y-axis, because I'm graphing x on it. Get it? So I'm going to refer to this as the vertical axis. Unfortunately, you already know that object A has motion that can be described like that. Right? You found the linear fit to a graph yesterday. So you understand that a straight line has that form. We good so far? But what's actually plotted on the y-axis?
Where it is.
Position. Yeah, that's what I want to use. I wrote it so we'd be able to say it together. So what's actually plotted on the y-axis? Position. Yeah, position's on the y-axis. So I don't want to call it the y-axis anymore. But I know that this has kind of been drummed into you for a lot of years. But the truth is, I should replace this with position. And what's being plotted on the x-axis, the horizontal one? Thank you, time. So instead of x, I'd like to write the word time. Yesterday we talked about what the slope meant for a position versus time graph. What did it mean?
Velocity.
It meant velocity, sure. In fact, if it were up to me, I wouldn't write it like this. If it was up to me and I wanted to write what was happening for A, I would say that A actually should look like x equals vt plus b. This is a relationship that talks to me about what is actually plotted on this graph. I know it's a straight line graph, so it has to have this, mx plus b quality to it. But m, x, and b all stand for something. In fact, what does b stand for? Yes, sir?
The y-intercept.
It stands for the y-intercept, or the vertical intercept. It stands for this point. Now, it means more than that here. This is a position. This is the position at time 0. What's another way of saying your position at time 0? Yes, sir?
The initial position.
The initial position. So I'm going to want to write this maybe x with a little I next to it. Is that okay for all of you? So, what I've created by looking at this picture of an object's motion is a motion equation. Motion equations tell us where the object is at all points of time in the future. This is not a particularly interesting one. This object is going to keep getting farther and farther away from where it started. That's all it is, because the velocity value is a constant. So if it travels for twice as long, it's going to go twice as far. That's not interesting, but at least it tells me to expect that. So if I want to know where it is in an hour or a day or a month, if it keeps doing what it's doing, I can tell you where it's going to be. Now, this was our first motion equation. Not particularly interesting, but still one nonetheless. There is something I do want you to see about this. It's pretty small, pretty minor, but if I subtract this from both sides, I'd get x minus x initial equals vt. We had a name for this yesterday. Do you remember what it was? Final position minus initial position. What's the word we used yesterday?
Displacement.
Displacement, that's right. Is there another way you can write this? What would be the symbology for final minus initial? You've answered a question. Let's try somebody else. Not that I don't appreciate you being so able to answer. All right, it's up to you there, buddy. You're the only one.
Delta x.
That's right. That's what I want to see. Delta x. Thank you. Yeah. That way we're using our terminology. The displacement of the object equals the velocity times the time. That is a motion equation. All right. Not a particularly interesting one. So let's turn this. I can increase the level of difficulty now, right? That was not hard. All right, so we're going to increase the level of difficulty. Good. I'm going to bring the same file up because I want you to answer some questions about this. And I really want you guys to talk to each other about this a little bit. I'm going to ask a series of questions about this picture again, but I'm going to put some labels here. First, this is the 5-second mark. This is still time. This is position. Sorry to bore you. And I'm going to put this in meters. This is going to be object A and object B, okay? This is 0 and this is 0. I'm going to ask a series of questions that I am not going to write down, but I will number them. Question number 1. Ready? If this were a race, who had a head start and how do you know? Think about the answer. Talk a little bit about it to each other. Make sure you feel comfortable because at this point, I'm not going to allow you guys to simply volunteer. I'm going to pick you guys by picking your tables and your symbols. I have chosen my first 3 volunteers. All right, time's up. So, Bikini Bottom. Pick a friend. Tell me tell me an answer. I'll let somebody at the table, anybody at the table.
B would have a head start because it's in a closer position.
Say again, I couldn't hear you.
B had a head start because it's in a closer position.
All right, so B has how many of you agree that B has a head start? All right, I'm not sure if I like the rest of her sentence, but that is the right answer. B does have a head start. In order to understand that, I'm going to look at time 0, which is these two places. They represent where the object was at time 0. Which object is farther away from the origin at time 0? B. That's why B has a head start. It's farther away from the origin. In fact, when I look at this, is it clear to all of you the objects are traveling away from the origin all the time? Is that true? You guys agree with that? So they're always traveling away from the origin. The one that started further away definitely had the head start. All right, next question. Who is leading this race at 7 seconds? Who is leading this race at 7 seconds? Does Winterfell have somebody who can answer that question?
It's A, right?
Are you asking or telling?
It's A.
First, why do you think it's A?
Because it's at a farther position from the origin.
All right, somebody else at your table needs to answer this question for me. Where's 7 seconds? I don't see 7 seconds. How is he saying it's a farther position if we don't know where 7 seconds is? Yes, sir.
5 seconds is like the point where A passes B.
Perhaps.
We know 7 is after that, so we know that A is pointing past.
All right, so we do know 7 is somewhere over here. That's a true statement that he said. Is there any time after the 5 second mark where A is behind B? So does it matter? No, not really. That's good. That's good. So you brought it up, so I'll ask the class. I would like you to tell me, when do these two objects have the same velocity? Think about it for a minute. When do these two objects have the same velocity? All right, you've heard the question. Talk about it a little bit. And I am ready. So, Earth. One of you has to answer that question for me. When do these objects have the same velocity?
Is it 5 seconds?
How many of you raise your hand if you think it's 5 seconds? How many of you just don't know? Be honest. Because I'm just going to go from table to table. All right. It is not 5 seconds. So, and I'm not trying to be mean to you. We talked about this yesterday, and this is a problem that a lot of students have. If I was to have given you a quiz, this is the quiz questions I was going to give you. Just so you know. I would have asked these questions. I think a lot of people would get this one wrong, especially on a quiz where they can't just bounce out their answers with the person next to them. And I think 5 seconds is the go-to spot because something is clearly happening at 5 seconds. But you have to ask yourself, do these lines ever have the same slope? Even at 5 seconds? It's important that you know they do not have the same slope ever. At 5 seconds, they are in the same place. This is the same location. But the lines don't have the same slope. It should be pretty clear that this line's slope is different than this line's slope, even at the 5 second mark. So they never have the same velocity. It was already said out loud, and I will reiterate it, that at 5 seconds, A passes B. That's what's happening at the 5 second mark. All right. Hitting the pause for a minute. Easy or hard, doesn't really matter. If it's easy to you, great. If it was hard for you, are you making some progress? Because I'm going to ratchet up the difficulty in the next segment. Can I do that? Before I do that, let's just take just a quick second to talk about person C. Tell me, when you see person C, would this confuse you if it were on the test, if this is person C? Let's make sure. I want a one-sentence explanation of how person C is different than A and B. And I'd also like a one-sentence statement of how person C is similar to A and B. Okay? I've got 3 more tables I've already pulled here. I'll be hearing from them in a moment. 2 sentences. How is C similar? How is C different? Bounce it around the person next to you. Ready to tackle this one? I don't want to spend a lot of time on this one because I don't think this is a big difference, but I think it's big enough to throw a few of you. So let's talk about it for a moment, okay? First, I would like it very much if you would take a minute and just write a description of what might be happening here. Hoth, give me your sentence. Somebody there describe it for me.
I said person A is running at a constant speed throughout the whole race, while person B starts out slow but gets exponentially faster and passes person A at 8 seconds.
How many of you would agree with what he said? How do you know that he is getting faster?
Because his position is going up a lot faster than his time is moving.
I was looking for something else. I was looking for a different explanation about how we know he's getting faster. Yes, ma'am?
His velocity is changing
How do we know?
because the line's curved.
Okay, keep going. One more thing.
Um,
Is the line getting steeper or shallower?
steeper.
How many of you would agree? Steeper, a good word there? Yeah. I don't know if it's exponential. Everything you said is perfect. I don't know if the word exponential needs to go there. Because I really don't know what the function is. It could be quadratic. It would look like that. It could be x cubed. It could be like that. So I don't know the function. That's why I don't want to use the word exponential. Assumes e to the x, or in this case, e to the t. And I don't know if that's true. I definitely know that the line's getting steeper all the time. We all understand that and see that. The line is always getting steeper. Is there ever a time where line B is not getting steeper while we're watching it? Now, I want to be careful about this because some people will nod yes, but they don't really understand what I mean by that. So when I say it's getting steeper, consider that I could look at tangent lines. For example, let me pick a point here. If I pick this point on the line, if I want to know how fast it's going, I would need a line that is tangent to that to get an idea for what the slope is. I know you guys know what tangents are. You had geometry. So a tangent to a curve meets the curve at only one point and needs to look like a tangent line. So I think tangent line. Can you see the red line? Is that tangent? I'm doing that because if I look at, say, this point right here, if I wanted to make a tangent for that, that a tangent line? Do these two red lines have the same slope? Is the second line steeper than the first? I think so. I think it's getting steeper. That's what I see. Now, I'm bringing this up because this object clearly is moving in a different way than the object we saw already. This object is changing its velocity. The word to use here is it is accelerating. I want to be careful about the use of this word, however. This word does not have an arbitrary definition. It has a specific definition. Acceleration is the rate that your velocity changes. And any change in velocity is due to an acceleration. Be careful. That is a deceptively complex statement. Any change in velocity is an acceleration. If I make a turn, my direction changed, that's an acceleration. I go faster, my velocity changed, that's an acceleration. I hit the brakes, my velocity changes, that's an acceleration. So be careful. Acceleration does not mean speed up. And I will never use the word decelerate in here. Accelerate and decelerate are not opposites. Not in this class. So we have to be careful. My vocabulary is very specific. Where is it most likely the two objects have the same speed? 2 seconds, 5 seconds, or 8 seconds? Raise your hand if you think it's 2 seconds. Raise your hand if you think it's 5 seconds. The 5 seconds clearly have it. All right.